Okay, so uh, we will start the class for chapter 6. All right. So last time we talked about the definition of the linear estimator. So on top of that, we have a description that is called true, meaning I'm sorry, the best. Something being best means minimum variance in this case. And then linear means that we are going to do a linear combination. So, uh, so I would, I would, yeah, recommend that you read some details for the contents here. Okay, but briefly speaking, we are having this estimated as a linear combination of the data. And one of the good example is that we have a DC level in WGN. And then in that case, we did it before. The sample mean is the best one, and it happens to be the linear operation on the data, and therefore, therefore, we have this equation that is the NVU, while at the same time is the best one, linear one, so it will be the blue. And on the other hand, if we are doing this uniformly distributed noise, it's going to be something like this. And by the way, how does this come out? It is not trivial, and it has to be done on example 5.8. So, but by skipping the details, we will just use the estimator to explain. Okay, so since this is the best estimator, but obviously it's not blue, right? It's not linear. It's not even linear. So we will say that this estimator is not BLUE. Okay, and then for another example, that is the power of WGN. And thus, we all know the solution is sigma squared equal to 1 over n summation x squared. This is also nonlinear in the data. Okay, so the point is, uh, we have a we have a good estimator. We already know it, but if we want to force the estimator, if we want to force the estimator to be linear, then it has to be in this form. It has to be in this form. So let's take a look what's going to happen if we take it to be linear. Then you take the expected value of the estimator, then it becomes 0. No matter what an is, be aware that an is not going to change the expected value. So uh, for this expected value to be 0 for all n, then we cannot even find a single linear estimator that is unbiased. As you know, if it wants to be unbiased, when you take the expectation, it has to be sigma squared. But now you get 0. Therefore, we cannot even find a single estimate that is unbiased, let alone one that has the minimum variance. So although the BLUE is unsuitable for this problem, a BLUE utilizing the transform data y equal to x squared will produce a viable estimator. So let's take a look at what happened. we do sigma square hat equal to summation an yn, and we let yn equal to x squared. Therefore, you get this summation an x squared. And the unbiased constraint yields, you take the expectation, then you take this expectation of this is equal to sigma squared. So what that means is this is an unbiased constraint. As a result, if you just take summation an equal to 1, then the whole summation will be equal to sigma squared, right? So there are many values of an that satisfy this constraint. But can you guess what the an should be to yield the BLUE? I guess we already have answers, right? An, if it's equal to 1 over n, then that would do the job perfectly. It will be unbiased and also minimum variance. So the answer is an equal to 1 over n. Then that would do the job. Okay? But of course, we know the answer, so we get this n1 1 over n into an, but you can try to practice one more time and see what happens. Okay, so let's take a look at from the perspective of as I say, the universe of estimators, the whole universe. You see there is this linear estimator and nonlinear estimator. And for the DC level problem, BLUE is in the linear region. Therefore, it's optimal and also linear. And then we can call it BLUE. And there are a whole bunch of other estimators in the nonlinear domain. And as you can see, there may be other things here, but it doesn't matter. We get the BLUE in the linear already. So we should be happy about that case. In this case, we're happy. We have linear and best, linearity and best. But for this uniform noise example, in fact, the NVU stays in the nonlinear domain. But when you are doing this linear estimators, it has to be a linear summation of linear combination of the data. A linear combination of the data. As a result, when you do BLUE, it's not the best one, right? It's not the best one because this is the minimum variance. But this unbiased one is in fact not minimum variance. It's not minimum. So BLUE will be suboptimal. Okay, so that will be the case. We have simple case and also a more complicated case where BLUE is not optimal. Okay, so to determine the BLUE, we constrain theta hat to be linear and unbiased, and then find the ANs to minimize the variance. So the unbiased constraint is from 6.1. You do expectation of theta hat. Let's take a look. 6.1. you do linear combination. Okay, so expect of theta hat equal to summation of an expect of this is theta. This is the constraint. And then unbiased constraint. And the variance is variance equal to this and this, right? We are doing variance on this term. And variance of this is supposed to be the random variable itself by the mean minus the mean of the random variable. And then take the parentheses square. So by using 6.2 and let a equal to this, we have variance of this. Well, in fact, we are writing this into a vector form. So you have a t x minus a t expect of x to the square. And expect of a t is taken out. And then x minus expect of x to the square equal to expect of a t, this, right? This a t x minus expect of x, x minus expect of x transpose and a. So you have a t c a. So how does this thing come out? We actually have expect of a, but a is a constant, so a goes out. This a is a constant, so a goes out. So you get expect of x minus e x, x minus ex transpose. This is exactly the definition of the covariance matrix, and therefore you have C covariance matrix. So the vector A of weights is found by minimizing this, right? Because we are going to minimize the variance. So if you find an A vector that minimizes this, then you get the minimum variance estimator. So what happens is we are trying to find an A that satisfies this and then minimize this at the same time. So before proceeding, we need to assume some form for expect of x. In order to satisfy the unbiased constraint, expect of x must be linear in theta, or expect of x is equal to Sn multiplied by theta, where Sn are known. Otherwise, it may be impossible to satisfy the constraint. Okay, so as an example, if expect of xn is equal to cosine theta, then the unbiased constraint is expect of this equal to an cosine theta, and it has to be theta for all theta. And clearly there do not exist an that will satisfy the unbiased constraint. Note that if we write xn as this one, and by viewing this as noise or this, then we have xn equal to theta xn plus wn. Okay, so we have this xn equal to this. The assumption of 6.4 means that BLUE is applicable to amplitude estimation of non-signal in noise. To generalize its use, we require a nonlinear transformation of data, as already described. So if you recall this, we actually have a transformation by this transformation of taking the square. So let's come back. The assumption means that it's applicable to the amplitude estimation. So we want to generalize it. With the assumption, we now summarize the estimation problem. To find a PLUE, we minimize the variance, right? We minimize the variance, which is described in terms of AT, C, and A. And then subject to a lot of things. First thing is, when you take the expectation, it has to be equal to theta. That's unbiased constraint, right? And then summation of an Sn theta has to be equal to theta. This is also unbiased constraint. And then summation of an Sn is equal to 1, right? Or in a vector description, ATS equal to 1. Okay. Then now what? You have an objective function with this constraint. So this is a typical optimization problem. You remember that? If this is not clear, then I recommend you to review. If you have taken a class of optimization, I think it's going to be very useful in this case. It's just a optimization problem. You are objective with some constraints. Okay, so the solution to this problem is derived in appendix, but this one is not difficult because in optimization we actually solve a lot of difficult problems. So this one is not a difficult problem in terms of optimization. So you have A OPT equal to C minus 1S over ST C minus 1S. Okay, so we solved A already. And the BLUE is, let's take a look. The BLUE is the summation of A multiplied by X, right? Summation of A multiplied by X written in a vector form. Then you put this into here and then take the X. In fact, the X has to be supposed to be here, but it doesn't matter. You put it in the numerator, mathematically equivalent. So, and it has minimum variance like this. So from 6.4, since expected X is equal to theta X, so the BLUE is unbiased. You take the expectation, you verify it. You see expect of X is S, and then we're happy those things are identical, so a lot of things cancel out and the theta remains. So if you have this respect of theta hat equal to theta, then you get good stuff. You get unbiasedness. Also, as we asserted earlier, to determine the BLUE, we only require knowledge only of S, or the scale mean, and covariance matrix. So as you see, you need S and covariance matrix on the first two moments, but not the entire PDF. Okay, so I think that that is for this session. We take a 1 minute break and come back.